Okay, so this is our introduction to stoichiometry, and you might have heard some stories about stoichiometry. It's kind of scary sounding word, but really it's just dimensional analysis, which should make some of you feel better. Some of you didn't do so great at dimensional analysis last time around, but this means we get another chance to hit it again. It really should be getting simpler as we move through it. If it's not, come in, let me help you with it, because it's not going away. So, pages 2 and 3 is what we're going to be working on today. We're not even going to do all of page 3. So it's really kind of 1.5 pages for our podcast. And also make sure you have your periodic table and a calculator out, because there's going to be a couple times I have you do some calculations, and even when I'm doing them, I want you to try and follow along. Push the same buttons, see if you can get the same answers. Because if you're not, either I made a mistake, which is possible, and I want you to help me fix it and get you recognized for that, or you made a mistake and I want to help you fix it and figure that out. So, one way or the other, let's get started. First off, we're reviewing molar mass. The most important thing to know about molar mass is that these numbers are the mass of the 1 mole of a substance. So back in Unit 6, we wrote out equations like this, and that number that we added up from the periodic table was how many grams of our substance was equal to 1 mole. So this was a conversion factor. We used this equation to convert from grams to moles or back again. So we're going to practice finding these real quick. We just find it on the periodic table if it's something simple like PB. So if I find PB on the periodic table, that tells me that it's 207.2. That's the molar mass. I just need to add the units. When the number is by itself, if I just ask you what's the molar mass of this, it needs grams per mole on it. Now, yes, I can pull this apart and say that 207.2 grams of lead is equal to 1 mole of lead and turn it into that equation form. But if I ask you just for the number, then we don't need to have those as separate kind of halves of this equation. So, number from the periodic table. If I have something like N2, it's still just one element, so I'm going to find N on the periodic table and its mass. But since there's 2 of them, we're going to multiply that by 2. And that gets us a molar mass of 28.014 grams per mole. If I have more than one element, I'd recommend you start by finding each of their masses separately on the periodic table. Then look at the formula to see how many of each you need. I just need 1 N, but I need 3 H's. So I'm going to multiply this by 3.024, and then our final step to finding the molar mass of this entire compound with that 1 N and 3 H's is to add up these masses, and that's going to get us a final mass of 17.031 grams per mole, of course. So, most of the time, it's that simple. The equations can get a little bit more complicated, but each time, just start by finding the elements and their masses, multiply them by however many you got. So I'm going to skip this K3PO4 because I'm pretty sure that you can count these atoms and set this up. I do want you to find this molar mass, and your answer should end up being about 200 and something, and remember not to round that number. We're going to take all the numbers straight from the periodic table, use them just like they are. We do not round molar masses. I want to jump over to this aluminum sulfate. It still just has these 3 elements, but counting them is a little bit harder. So I'm going to start actually just by finding each of these masses. And now I'm asking myself how many aluminums are in this formula. Well, that one's pretty straightforward. There's a 2 on it. So I'm going to be multiplying this by 2. Now, when I look at my sulfur, because that's in parentheses, then I need to distribute this 3 from the outside of the parentheses into the sulfur and the oxygen. So that's going to multiply by how many there already are inside the parentheses. So it looks like there's 1 sulfur, but 1 times 3 means I actually have 3 sulfurs. So, and then when I look at my oxygen, it looks like there's 4, but with the 3 outside, that means that there's actually 12 oxygens. That's a lot. And these numbers can get kind of big, but as long as you take it step by step, we found all the elements by themselves, multiplied it by however many there are, and now our last step is to add up these masses. Gets us a final mass of 342.15 grams per mole. So make sure that you do that potassium phosphate example. Like I said, should be 200 something. So that's molar mass. We've done it before. Let's get into stoichiometry. Stoichiometry is comparing mole ratios of elements in a chemical reaction. It's technically a Greek word. Stoichio means element, and metry means measuring. So it's all about measuring elements and reactions. Now we're using a mole ratio. What's a mole ratio? It's a conversion factor written from a balanced chemical equation that relates the number of moles of two substances. I wish I could have gotten that to fit on 2 lines, just didn't quite have enough space. Maybe you can fit it on 2 lines. You got more space than I do. But the short answer is we still need to be able to balance equations because we're going to be using those coefficients, those numbers from the balanced equations to set up ratios. Kind of like what you did with the cookie stoichiometry activity, just pulling out the stuff that you want to put together in a ratio and taking the number and the kind of units that go with it and just setting them equal to each other. That's a ratio. So we're just going to be making mole ratios this unit. Now, we're using those mole ratios to solve and figure out how much of this I'm going to make or how much of that I need to use. And it's important that you realize up front that these are theoretical yields. These are calculated amounts of how much product could be made or how much of the reactants I might need. But sometimes chemistry doesn't happen perfectly. It doesn't all go according to plan. So this is all theoretical. When we get back and actually do a reaction in the lab, it might not happen quite this perfectly. But we'll address that in the next big idea after we practice this stoichiometry stuff for a little. So I've mentioned that this is like dimensional analysis, and some of you struggled with it, but one way or the other, we're doing the same type of thing. And you might recognize this map from back in Unit 6 when we were converting from mass to moles to particles. Well, we're doing that same thing. If you look at the front of your packet, we have those same mass to moles, particles. It's just all of the same substance over here. Then I have mass, moles, and particles of a different substance B over here. So it's that same conversion that we were doing before. Here, it's just technically 2 of them in the same map, and they're connected by this mole ratio idea. Mole ratios help me convert from moles of one substance to moles of the other. Now, this I did cut off the bottom bit because we're not going to get to that yet. That'll be in unit 12 or something. And the good news is this map on the front of your packet is also a little deceptive because we are not going to deal with the particles at all either. That Avogadro's number, that big crazy scientific notation number, we are not going to use at all this unit because this is all about being able to measure these elements and compounds in real life in the lab, and we don't have a scale or anything that can measure and count those in real life. So it's really just going to be this center section of this map that's on the front of your packet, but that's even kind of a bit messy. So I made my own. This is our map. Just like what you saw on the front there, we can go from mass or moles of our given substance, one substance A, and we can convert it to either moles or mass of our unknown substance B. And the key to converting between these two sides, these two different substances, is our mole ratio. This is technically the only new thing that we're doing. This molar mass to get from moles to mass and back again is the same equation. I just have to make sure, because I'm going to be dealing with 2 substances, sometimes I'm going to need the molar mass for my first substance, sometimes I'm going to need the molar mass for my second substance, and in some problems I'm going to need both. But regardless, those molar mass numbers just come from the periodic table. So we just add those up like we practiced at the top of the page, turn them into an equation when we need to use them. The only other thing that I'm going to need here is our mole ratio. Every single stoich problem is going to use a mole ratio. And so I need to start with a balanced reaction and pull out the chemicals that I care about and just put them equal to each other. This many moles of this is equal to this many moles of that. So these are the biggest problems that we might have, is a 3-step problem to go from mass of this, and have to go to moles of that same thing first, then switch substances to moles of that other thing, and then get mass out. So 3 steps is our biggest problem. But we're not going to start with the biggest problems. We're going to start with the smallest problems. Here we're going from moles to moles. And let's go ahead and fill this in. We've already said it once, maybe twice, maybe a few times, but a balanced chemical equation is needed in order to do these. So anytime you see a reaction, balance it. But when we think about these problems that we're starting with, the fact that they're from moles, I'm being given moles, and you can see here my given is 15 moles of carbon dioxide, and I want to know how many moles of potassium carbonate are needed to react with that. So if we look back at that map, this section right here is just given moles, trying to find moles. All I need to get between these two things is our mole ratio. No molar masses yet. So let's get started. This is our given, like I pointed out before, 15 moles of carbon dioxide. And now that we're going to be converting between substances, we do need to include the substance in that dimensional analysis set up here. So number, unit, and substance now in every single part of this dimensional analysis and in our answers. Now, I need this to be balanced, and it's kind of lucky for me that this is balanced already, but I'm going to write the ones in because I'm going to be writing the ones in my dimensional analysis. So that'll help me realize it is balanced. So, just like every other dimensional analysis problem, whatever my given units are up here are going to be the same units on the bottom of that next bracket. The only difference is I'm not bringing the given number with it. This number is the number that's going to be in my mole ratio, and that comes from my balanced equation. So what's the number in front of CO2? 1. So 1 mole of CO2 is equal to, what substance am I trying to find? It asks for potassium carbonate here. So I want moles of potassium carbonate on top, and the number in front of that is also a 1. So the math here isn't hard. The point of this is to practice setting up these units. Whatever is given goes on the bottom of the next bracket. In order to solve this, if you don't remember, we multiply any of the numbers that are left on top, so 15 times 1, and we divide by any numbers that are on the bottom. So 15 times 1 divided by 1 equals 15. And like I said, the math here isn't hard. It was more to practice the process. And what has happened here is that our units have canceled out because I had moles of CO2 on top and on bottom. They've now gone away, and the units I'm left with is moles of K2CO3. So that is my full, complete answer. And this next question, I do need to balance this a little bit. Put a 2 there to balance 8 O's, then H's. So this is 2, 1, 2. My given here is 5.55 moles of hydrogen. So I know I'm going to be putting moles of hydrogen on the bottom here. And this time I'm going to be putting a 2 with it. This is the first time that you've ever put a number other than 1 with the moles. But in our mole ratio, those numbers come from the balanced equation. So we just follow that. So that's 2 moles of hydrogen on the bottom. And I need to figure out what other chemical I care about. So I'm going back to my question. It asks how many moles of water. So I also care about the water. And I'm going to bring those 2 H2O's down, just making sure it's a mole ratio by including the moles in that ratio. And so now units of moles of H2 have canceled. I have moles of H2O, which is what I wanted. So I'm ready to stop and calculate. And here I'm doing 5.55 times 2 divided by 2. And this turns out to be 5.55 moles of water. Once again, the math isn't hard yet, but just focusing on this setup and where we're finding these numbers. So let's move on to one where the answer isn't going to be the same as the given. So this starts with 5.55 again, but if you read carefully, that's 5.55 moles of oxygen. And even though this is the same reaction as before, I'm going to rebalance that. So now if I have moles of oxygen on top, then I'm going to bring this 1 mole of oxygen to the bottom, and I'm still looking for moles of water. So I'm going to put 2 moles of H2O on top. So units on top, units on bottom cancel, moles of water is what I want. So I'm ready to do 5.55 times 2 and then divided by 1. And the divided by 1 part won't change anything. So in my calculator, I'm pushing 5.55 times 2, and that's 11.1 moles of water. So, next question, number 4. I want you to do this one. Set it up, work it out. This is going to seem like it's kind of a small number, but we already started. Our given is a small number here. So I'm going to go ahead and balance this reaction just to make sure that that's not what's going to hold us back. So we've got these coefficients here. We don't need any molar masses. Just take your given and use the mole ratio from this reaction to set up and solve this problem. I am going to hold back a stamp if you don't try to work this one out. Okay, real quick at the top of page 3, we're going to work 2 more problems together, and then I'm going to ask you to try a third. So these problems start to introduce mass. So we're going to be doing more than just that little one-step conversion in the middle of our map now. Now we're going to have to find the molar mass, either of our given or unknown substance. And the way you know what to find the molar mass of is to look at which chemical, which thing has grams in the problem. When we're reading through this first problem, this says I have 6 moles of magnesium. So that's moles. That's just kind of normal, like we had done before. And then it asks us, what's the mass in grams of our oxygen? So oxygen is the thing that I need to find the molar mass for real quick. And so oxygen is O2. Each of those oxygens is 15.999. If I multiply that by 2, that's 31.998. And of course, we would put the units grams per mole on this, but because we're going to be using this for dimensional analysis and stoichiometry, I'm going to go ahead and write that out as an equation. Remember, we're going to pull apart the 2 halves of this, and we're going to say 31.998 grams of oxygen is equal to 1 mole of oxygen. This is how I'm going to actually be using this in my problem. So let's go ahead and start setting things up. I have my given is 6 moles of magnesium. And even though I know I'm going to need this molar mass equation, I can't use it yet because I have moles of magnesium here up top. So I know I need moles of magnesium down on bottom. So I can't use that equation yet. I'm going to have to look in my balanced equation, which might be helpful if I balanced it. Oh, look, another 2, 1, 2. So when I'm trying to figure out what numbers to put with my magnesium, this time it's going to be 2 down there on the bottom. I'm trying to find oxygen, so I'm going to put that 1 mole of oxygen on top there from the balanced equation. And now I'm not ready. I have oxygen, but I don't have mass. I don't have grams. So I'm going to have to keep going, make my line a little longer. And now I see something that I can use for my equation. I can put this 1 mole oxygen there, and then my molar mass, 31.998 grams of oxygen, is going to go on the bottom, on the top. Wow, that other side. So now that I have grams of oxygen right here at the end, and I can double check that everything else cancels out on those diagonals, I'm ready to stop and calculate. And then I'm going to have a few more numbers to put in my calculator, because I'm going to take the 6 times 1 times 31.998 divided by 2 and divided by 1. And I would really recommend that you do all of that together all at once, push equal once, and get your answer out. This answer is going to be 95.994. And technically, we only want to keep 3 sig figs here because my given only had 3 sig figs at 3 and the 2 zeros. Or sorry, the 6 and the 2 zeros. And 3 sig figs means I want to just keep those, but the 9 is going to round this 9 up. So my final answer is going to be 96.0 grams of oxygen. This next problem starts with moles and wants grams again. So even though it's different substances, and this is a different reaction that also happens to be a 2-1-2 reaction, it's going to look a lot the same. So let's go through this process, starting with the 1.33 moles of chlorine. When I have moles of chlorine, I know I want grams of sodium chloride. If I add up Na and Cl, then that's 58.443 grams per mole. But I'm not quite ready to do that equation yet, because I'll do it in a different color. That's all about sodium chloride, NaCl. And right now I have Cl2, chlorine. So when I am ready, that's going to be 58.443 grams of NaCl in 1 mole of NaCl. I really hope you have more space on yours than mine. So if I can't use my molar mass yet, I'm going to have to use my mole ratio. So if this is chlorine on top, I'm going to put this 1 mole of chlorine on bottom. I'm trying to get to NaCl, so I'm going to put 2 moles NaCl on top. Now I have moles of NaCl. I can use these moles of NaCl. So this 1 goes on bottom, and the 58.443 grams of NaCl goes on top. So this answer is going to end up being 155. Technically that's 0.4, but that won't round the 5 up, and that's going to be grams of NaCl. And if you look at these two problems side by side, you can see I start with moles in each of them. The next thing I do is my mole ratio, and then I have this molar mass with 1 mole on the bottom and the molar mass on top. So these two equations, these two setups for this stoichiometry is pretty much the same, except for the elements involved and the numbers that go in those equations. So they're pretty similar, but they are going to be unique to each. And if we just look back real quick, then in each of those situations, we were going from moles of our given to mass of my unknown. And the first thing I did was use my mole ratio, and then I used my molar mass of that unknown substance, the second substance. So that's why they look the same. The next problem that I'm going to ask you to do and try, and I'm not going to hold the stamp back if you don't get it, is mass to mass. So it's going to be the same 2 steps, but before that I'm going to have to start off with the molar mass of my given substance in order to get from grams to moles, and then get from moles to mass again. So I do really want you to try question number 7. I'll balance this for you just in case, that might hold you back. If we focus on our C's and H's, and that balances our O's. So 1, 5, 3, 4 are the numbers. I want to try and see you set this up and work this out. If you can work this out, I'll give you 2 stamps on this page. But your answer should be about 180-ish. If I rounded it to a whole number, it'd round to 180. But technically, we should be keeping 4 sig figs because our given here has 4 sig figs. So give it a go. See if you can get it right. If you can't, then we definitely got to work on some stuff together next time. If you can, next class is going to be super easy for you. So that's it.